acceleration. So in that situation, I want to determine average acceleration. Okay. So V2 minus V0, it will be 20 minus 0 divided by 2 seconds. And again, you see that 20 minus divided by 2 is giving me 10. So here in this case, you are seeing instantaneous acceleration and the average acceleration, both of them are the same. So this is a very special case because whenever the acceleration is constant, this will happen only in that part. Okay. Now look at the last equation when we are deriving them, that here the average acceleration, comes out to be V minus V naught divided by T minus T naught. But what we do here in this case, that we can say that T naught equal to 0, right? So T naught equal to 0. So for that purpose, you are writing that the average acceleration V minus V naught and T minus T naught. So the last time you are starting from your 0 seconds, whenever you are considering this as the beginning of your observation or your experiment. Okay. So when you want to simplify this equation, since you left with the T in the denominator, all you need to do is to multiply T to the both sides, like as I'm doing this on the board, and please follow this one example, and then afterward we are not deriving equations. Okay, I'm just showing you the equations afterward. So T naught, we put it to be 0, so we left with the T in the denominator, and now I'm multiplying T with both sides, so AT equal to V minus V naught. This is the equation. I can keep the equation like this, or I can move the velocity to the left side, and I will left with the V naught plus AT, and that is equal to V, final speed. So this is one of equation of motion for the constant acceleration. Okay. So
I have a question.
Yes.
This equation, we only can use it with the constant acceleration, or with any acceleration question?
Not any acceleration. It is strictly applicable for the situation in which the acceleration is constant. Okay?
Okay.
If it was not constant, then you do other way around. Like, recall that in the recitation yesterday, I shown you that if there were two accelerations, one case the car was accelerating, and the second it was decelerating. So if you look at the two parts, the acceleration is not the same. So what we did, we split that equation, that problem, in two parts. We solved it for the part in which the acceleration was constant, separate than the other part. And so that's the second way of approaching to that. Okay.
Okay. Thank you.
Yeah, and then at the end I will be showing you when the situation is even worse, like a lot of variation is happening. So there will be graphical method applicable for that. So this is my first equation of motion that I'm having here. For the other equations, I'm not deriving because it takes time, and the students usually don't enjoy derivation. So here, this is the average acceleration equation. And these two equations, like the way in which I have described, everything is uploaded on the slides to the Blackboard. You can see and let me know if you did not understand any step. So I'm skipping this slide and getting into the final equations. By following that method, in the last slide, you will get into the equation derivation. So this is one of the equation which we already derived, and you are seeing on the board. This is the second equation, which we call it the quadratic with respect to time, right? And then this is Vf square equal to V naught square plus 2ax. This is another equation. This equation here, which you see in the second row and the fourth row, in the fifth row, these equations are exactly almost the same equations. But if you look at the first term, here you have V naught Vt, and here you have V naught t. And here you have plus sign, and then you have here negative sign. How it comes, when you put this, when you try to eliminate V naught between this equation and this is what you will get, which is the fifth equation. But the long thing short, let me just conclude what we want to say here. These are the equations on the left side, and these are the missing quantities in the equation. So assume that there was a problem was given to you, and in there they're asking you to determine acceleration. So acceleration is the quantity which you need to work for. Initial speed, final speed, and the time duration is given to you. Okay? Initial speed, final speed, and the time duration are given, but the acceleration is unknown. So in that case, you got to use this equation, because if you start to use this, or this equation, all four of the equations, along with the acceleration, there will be a displacement also unknown. So you don't want to bring any other unknown to your equation. You can afford only one unknown in one equation. Okay, so this is the way in which we are approaching to it. So I will be solving some problems, and hopefully you can see that.
Doctor, for V naught, it means
The final equation gives the position of a particle in four situations, situation 1, 2, and 3. To which of these situations do the table 2.1 apply? So here we need to look at something. You know that this table, all the equations are derived, strictly speaking, for the constant acceleration situation. Okay? If the acceleration was variable, means it was dependent on time, then we cannot apply this. What we need to do is to look at this displacement equation and take the derivative of this 2 times with respect to t. And what do we get? You see that in the part A, when we apply 2 times derivative of to this equation with respect to time, we are getting 0. And here we get minus 30t plus 8. And similarly, this equation and the last one is 10. Among the four equations, which one you think giving us a constant value for the acceleration?
The first and the fourth.
Is the first one a constant value?
Yes, 0.
0 is a constant. Yes, it is. Don't be shy in saying it there, right? 0 is constant. And then how about the fourth one?
Yeah, it's constant.
Yes.
10.
It is also constant.
Yes.
But if you look at 2 and 4, they are time dependent. Means if you have 1 second, then you will have one kind of answer. If you have 2 seconds, then you will have 2 different kind of answer. So with each passing period of time, the acceleration will be different. So therefore, we cannot use the equations used in table 2.1 to the situation given in 2 and 3. Those equations are applicable for situation 1 and 4. Okay, let's do this problem here. That this equation gives the particle velocity versus its position as it moves along an x-axis with the constant acceleration. What is its velocity at x equal to 0? So we want to determine the initial velocity, and you cannot really assume that it is 0, right? Because it's not 0. So what we need to do, we need to split this problem in two, because look at this problem. It is again a graphical problem here. Velocity is given on the y-axis and the position is given on the x-axis. So position and the velocity, these two are the known quantities in it. Apart from that, if you look at that, we don't have any acceleration. Okay, the acceleration is not known, and they are still on top of that. They're asking the initial speed, so we need to work for it. What is the suggested solution? Look at this one. First of all, you need to consider the second part of the problem, because right here we know exactly for this situation when the particle goes from 20 to 70, the situation is known, because initial velocity is 8. If you look at the final velocity, it comes out to be 0. Okay. We also know that the x position here is 20 and the x position in there is a 70. So we need to plug in those values and determine the acceleration from it. we get minus 0.64 meter per second square. And quite rightly, it tells us it is negative because the particle is coming to a stop, decelerating. Now, in the second part, since our concern is about the initial speed, what we need to do is that you can either, there are two choices to make. You can either choose this section in which the final speed is 8 and the initial speed is unknown. Okay. For that, the x naught will be 0 and x is going to be 20. If you're going with this problem, then this is what it is displayed here. The answer, you are getting it to be 9.8 and 9.5. But you can also choose that I want to consider the entire curve, and for that, the initial speed is not known, the final speed is 0. So you will put, instead of 8, you will put 0. But the x is 70 and x naught is 0. So in that case, you can apply again, and you will get exactly the same answer as we got here. So both cases are giving you the same answer. It's up to you which one is easy for you. You choose that.
Teacher, can you go back?
Yes. Any quick question?
Yeah, the teacher, from the shape of the graph, I don't think the acceleration is constant.
Acceleration?
Yeah, I don't think it's constant from the shape of the graph.
The shape of the graph, it tells us that it is constant, but you need to know that it is not the velocity versus time graph, which we normally got used to it. Okay, if it was velocity versus time graph, then yes, it appears to be a straight line. But here, since it's a velocity versus position, which is a little bit unusual, so yes, it is constant, but the graph appears a little bit weird because the quantities are different. Okay.
What's X naught present?
What is that?
What does X naught and V naught represent?
V naught is the initial speed, and x naught is the initial position, and it depends on your situation. If you consider this part of the problem, like which is on this right side, for that, your x naught is 8, and your your x naught is 20, and x is 70. And here, x naught is 8, and v is 0, right? V naught is 8, and v is 0. Did you get it?
Okay,
It
so
depends. It depends which situation you want to consider. Yes.
So I choose the point I want to know.
Exactly. You can choose any point. You can choose either this point if you want to. But for that, you need to work, okay? You need to put the graph and get the parameters. Since you know that it is 0 and this is 10, so it will be 2, this is 4, this is 6. So by that, you also need to make those considerations.
Okay, thank you.
Okay. So let's get into the free fall. And as I mentioned, that the free fall is nothing but it is a constant acceleration. But now this acceleration, since we know that if I release this marker from my hand, it will go towards ground. It doesn't go and this doesn't fly upward, right? It comes downward. And this is called a free fall because it is just falling under the influence of gravitational force, which in normal words we are calling it weight. Okay. This acceleration is considered to be constant, 9.8 meter per second square. So for most of the cases that we will be discussing, like falling something from the top of top of the building, or falling something from like a 500 feet or something, in that range, the G is almost constant, it is 9.8. But if we start to talk about the satellites, we are saying that we are shooting satellites to outer space and the gravitational acceleration on them is 9.8. No, that will be wrong. Okay. So the gravitational acceleration is 9.8 for our practical situation that we are dealing with on this Earth here. But if you are talking about the space, it changes. Now, here in this diagram, what you see, there is a feather and there is an apple. Ideally, our mind will perceive this information such that if I release an apple and a feather, both of them are falling, but the apple may hit the ground first and the feather will be hitting the ground later. That's what our mind is telling us, because our daily life observation involve the air influence in it. And if we do it at our home, yes, that will be the situation. But when you do this in vacuum, there is no air inside, and you release a feather and an apple, both of them will hit the ground simultaneously. Okay, so that's one thing. Because both of them are accelerated by the same amount, that is 9.8. Another observation is that here, these are the images after the same taken after the same interval of time, and you see that the distance between this feather image and this feather image, they are telling us that they are very close, and as the time passes, the distance between them increases. And that is obviously, you know that since objects are accelerating, so with the same interval of time, later on it will cover more distance, right? So for example, you're going with 100 kilometers per hour in your car, you will cover more distance in 1 hour as compared to you're going with the 5 kilometers per hour speed. Okay. One last thing to know more about this is the equation that we derived are shown you in the table 2.1. Those equations are exactly applicable as it is to the situation of free fall. But the only change you are going to make here, this is the equation as I'm putting here. So you know that it is V naught plus AT equal to V. All I need to do is to replace this A by minus G. A equal to minus G. Once I do that, this equation will be for free fall. Okay, so V naught minus GT equal to V. This is the equation for the free fall. Now you see the difference between these two. All I did, replace acceleration by minus G.
I have a question.
Yeah.
Why negative G? Is that because the direction?
It's because of direction, and also is because of the books. There are books that are having their own preferences. So Holiday Reasoning Crane, they are taking the preference of -8. So what it does that if you look at this situation like as they are talking about that if the object is falling towards ground, we will be considering G minus 9.8. Okay, in reality, that's what they're saying. Okay, if the object goes upward, we will be putting another negative here, then that will become positive, and then you are seeing it is that the object is actually the upward acceleration is 9.8 plus 9.8. So this is the book choice. In a lot of other books, what you will see that they are considering the G for the object when it's falling towards ground plus 9.8. And if the object is going upward, that is 9.8. Okay. So it is just the convention, but whatever convention our book is telling us, Holiday Reasoning Crane, which we follow, our textbook. Once we make this convention, we should be consistent for all the parameters that we are using. So look, this checkpoint is describing that situation even better. If you toss a ball straight up, what is the sign of the ball? A ball's displacement for the ascent from the release point to the highest point. So when you toss it, the ball goes upward. So in that case, what should be the sign for the displacement? What is your guess? What should it be?
Positive.
For
Positive, because here you see here this with the XY axis is, and consider yourself sitting on this platform. So if something goes upward, they are going in the positive Y direction. If something coming down, they are coming below your platform, then that will be obviously in the negative Y direction. So yeah, so based on these, in which direction they are moving, plus Y and negative Y, we will be assigning the sign to the displacement accordingly.
Is there a velocity? Is there a velocity where the g will go below 9.8?
What is that?
Is there a velocity where the g will go below 9.8?
Yeah, it's just the G9 below means you are considering negative, right?
No, like if I throw a ball from the furthest space, does it just go faster and faster and faster to reach this 1 million meters per second, 1 billion meters per second, or is there
No. It won't go. There are other components to look into that, because there are a lot of other things, which is called terminal velocity. So terminal velocity is another consideration. Okay. Because the real life scenario is quite different than what we are ideally discussing and considering. So the air is there, and there is a drag force out of that, and that's why the object cannot exceed some of beyond certain acceleration. Speed. Okay. So what is part B? What is for the descent? What is the sign of the displacement for the descent? Can someone tell?
Maybe it will be 0.
No, for the descent, the sign of the, when the object is coming downward, what will be the sign? Negative. Right. And what is the Ball's acceleration at its highest point?
0.
G.
No.
Minus
It is again G. It is 9.8 meter per second square. And then right there, even though when you look at from the perspective of the speed right there, then you are seeing, well, when the ball comes in to stop right there, there is no velocity associated with it. So therefore, there should be a 0 acceleration. But no, this is a gravitational acceleration, and the weight of the object right there is not finished, right? There is some weight of the object right there. So that's why there is this G at the highest point as well. Okay. A lot of things will be cleared when I do this example. It's a very extended example. A pitcher tosses a baseball up along y-axis with an initial speed of 12 meters per second. How long does the ball take to reach its maximum height? Okay, so let's see in the whiteboard here. What do we know? What is the initial speed?
12.
12. What? Okay. What is the final speed?
0.
0.
And what is the acceleration?
Minus
Negative
G.
9.8, right?
Minus.
Okay. So once you have this data, they are saying that how long it's going to take. You apply the equation of V minus V naught equal to minus GT, right? Okay. So in that case, here they are looking for time, so I need to divide both sides by minus G. So V minus V naught divided by minus G, and now put the values. V is 0 minus 12, because they are saying it is speed, right? They are not talking about the velocity either. And then 9 minus 9.8. So you know that this 0 is nothing, but let me clarify this now. You have negative sign and negative sign, negative will cancel out, and you will get some time out of it. Just calculate this. So 1.2 seconds, that's the time it will take to reach to the top. Now let's look to the second part of the problem. What is the ball's maximum height above its release point? So they're asking for which height it should attain. Okay, you're familiar with the equation of motion. Which equation of motion should we use now?
X minus X V naught equal to V naught multiplied by T plus half.
So H, let's say for height we are using H V naught T minus half G T squared. So this is the equation we are going to use. We know that the object, since it is going upward, we need to determine that. It's not known. But the velocity, the initial velocity is known, which is 12. The time we know it by now, it's 1.2 minus half, 9.8, and again at 1.2, and then you make it a square. Again, it's just a calculation now. You need to do this. So this is what we use one method and they're using another method. Both of them are fine. One equation they're using, one equation I'm using. Both of them should give us the same results. Okay. So this is the height to which the object reaches.
Doctor.
Now, interesting point is, how long does the ball take to reach a point 5 meters above its release point? That is something more interesting. So you know that when I throw the ball upward, I know the initial speed, but I don't know what is the speed after 5 meters, because the maximum height, you already know that it is reaching quite high, like 7.2. So the ball is still traveling. I don't know the final speed. This is one of the situations now I need to decide which equation in particular I'm going to use. So I will make use of the same equation again here, because the final speed I don't need in this situation. So they are saying 5 meters, so I'm putting 5 meters here. 12 times the time is unknown. I will put t, half 9.8 and t square. Let me rearrange this equation once more, and then you will be seeing that we have half, negative half, 9.8 t square plus half t minus 5 equal to 0. What kind of equation it is?
Quadratic.
Quadratic equation. So whenever you have a quadratic equation, you are solving them, you know that it will be minus b plus minus b square minus 4ac divided by 2a. So that will be the equation. Like, this is the equation we choose, and these are the detailed steps which you are seeing on your slides. So this is where I have reached, and after that you need to apply the quadratic equation. So when you apply quadratic equation, you are seeing in this formula, you have one value for the positive value and one for the negative value. You got the plus and minus. Okay? And here the time is either 0.53 or 1.3. So yesterday a student asked me, how can we decide that this time I should consider and eliminate this time? What do you guys think? Should we consider both times or one of them?
Substitute in the equation and you will get.
Okay. And any other student who wants to come in here?
Both.
Take the positive. Maybe.
Why we are going to take both?
Because one is going upwards and one is coming downwards.
Okay, there's the thing. Since they are talking about the 5 meters above its release point, so they are not saying that whether they are talking about the initial path or the final path. So when it is going up, it passes through that height once, and then when it is coming down, it also passes through the same height once more. So therefore, we are going to consider both of the times.
I have a question.
Yeah.
What if the initial height is above 5 meters? So we should don't take both?
I would excuse at this point. Okay, let me. I have 2 minutes, and let me talk about this final topic here. The graphical integration in motion. I told you that the situation which we have discussed so far, that was strictly speaking for the constant acceleration. Whenever we have a situation in which the acceleration differs, changes from one point to another, so it will be considered variable acceleration. What we need to do in that case, we need to integrate, and probably you are not familiar with the integration method, but if you have a derivative, you take the integration of both sides with respect to t. This is the shape of the equation that you are getting, okay? But we are not solving this by applying the integration methods. What we are going to do is, this thing inside the integration sign, this sign is the integration sign, and AT, what it giving us? AT. You know that one side and two sides. If you know the two sides of a rectangle, you multiply with each other, you get the area under the curve. Similarly for the triangle, similarly for the square. So what you need to do is that you need to determine area under the curve. Like here, you have acceleration on the y-axis, and you have the time on the x-axis. What you need to do is to determine area. If this graph was given to you, you see that there is, you can split this one. It's a triangle on the left side. From here to here, it's a rectangle, and again on the right side, it is a triangle. So all of them in total, we need to split, and it will give us the area under the curve. The same happens with the velocity. Velocity, we are also not going to integrate it, but rather we will be going to the two parts, looking for strictly the area under the curve. And this is one of the classical example of that. Okay, so I don't want you